So hello everyone, and welcome back to another video. Today I'm going to take about a paper called Stock Market Trend Analysis using HMM and LSTM. I will be implementing this paper. The link to paper and code is linked in the description box. So let me tell you more about this paper, and then we will start coding. The Hidden Markov Model HMM is a signal prediction model which has been used to predict economic regimes and stock prices. This project intends to achieve the goal of applying machine learning algorithms into stock market. The long short-term memory model LSTM ensures that the previous information can continue to propagate backwards without disappearing as the hidden layer continuously superimposes the input sequence under the new time state. Our main purpose is to predict the ups and downs of one stock by using HMM-LSTM. So now, let's start coding. The provided Python code is involved with loading, processing, and evaluating dataset features using machine learning models, specifically Hidden Markov Models HMMs. It uses libraries such as Pickle, NumPy, and various custom modules from a package called Dataset code and a module public tool. Initially, the script disables warnings to keep the output clean. The main process begins by loading a dataset from a Pickle file. It assumes that the data has some form of structure, as it proceeds to apply a deduplication function, dfconc, to the data frames columns. Next, the code extracts a list of features starting from a specific feature named Accounts Payables T-Days until the end of the list. It then initializes a score record array to keep track of the evaluation scores of the features. In a loop over all the features, the code prepares a raw dataset for each feature with certain parameters, filtering out any features without labels. Each feature is subjected to a process using an HMM, solve2, to classify data points and then used to create a training dataset. A model is formed using the training dataset and specific parameters for the HMM. Each model is evaluated using the evaluate plot function, which presumably assesses the model's performance and returns a score. The score for each features model is stored in the score record array. Finally, the scores in the features list are saved into a Pickle file for later use. This record keeping ensures that the evaluation scores can be reviewed or utilized in subsequent analysis without rerunning the entire process. The overall purpose of this code is to process a dataset through deduplication, feature extraction, training via hidden Markov models, and scoring the performance of these models on a feature-by-feature basis for further analysis. These steps could be part of a larger workflow in a machine learning pipeline, particularly in scenarios where time series data or sequential data is involved, which is typical for applications of HMMs. The provided Python script is designed to train two different types of statistical models using separate modules imported from a package called train model. The script's purpose is to execute the training process for a hidden Markov model HMM and a long short-term memory LSTM neural network when it is run as the main code. When the script is executed, the if name equals main block ensures that the model training functions are called only if this script is being run directly, not when imported as a module in another script. Inside this block, the script first sets the variable n states to 3, which is likely the number of hidden states desired for the HMM. The function train HMM model n states is then called, importing from the train HMM model file inside the train model package. This function takes the number of hidden states as an argument and proceeds to train the HMM with that configuration. After the HMM training, the script calls the function train LSTM model with no arguments, signifying that this function may have its parameters set inside the function or use a predefined configuration. This function comes from the train LSTM model file within the train model package and is responsible for training an LSTM model, a type of recurrent neural network known for its ability to remember long-term dependencies. In summary, the script is a simple automation tool for training two machine learning models, an HMM and an LSTM, likely for sequence modeling tasks such as speech recognition, language modeling, or time series prediction. Each model training function is defined in separate files and imported for use in this script. This Python code defines a function, combine, that is intended to combine data from two sources and provide a filtered result based on some conditions. The function takes 6 parameters, two inputs x1 and x2, which can either be lists or arrays. Two corresponding allow flags, allow flag 1 and allow flag 2, which are used to indicate which elements of the inputs are permitted. A label array that categorizes input data, and lengths, which seems to define segment lengths within the combined data. The function initially checks if x1 and x2 match in type with their corresponding allow flags. If not, the code exits with an error message. If their types are consistent, the function proceeds. The function then initializes an empty array x and an allow flag array with zeros, both of which are intended to be filled with combined data from x1 and x2. It determines whether the input data comes in list format, and accordingly loops through the lists to stack the data horizontally in the X matrix, and accumulates the corresponding allow flags. If the inputs are not lists, it performs similar operations without looping. The accumulated allow flag array is then processed to create a filter, setting the flag to 0 where the element count is less than the number of inputs combined, and to 1 where the count is equal to the number of inputs. Next, the function creates an empty matrix, result x, and an array, result label, along with an empty list, result lengths. It then loops through the entries specified by lengths to slice x and allow flag into segments, and uses logical conditions to filter these segments based on the allow flag and label conditions, excluding elements labeled as -2. It combines these filtered segments into result x and result label, respectively, and computes the lengths of these segments to populate result lengths. Finally, combine returns 3 processed and filtered results, result x, result label, and result lengths, which contain the combined data satisfying the specified conditions, the corresponding filtered labels, and the lengths of the filtered segments, respectively. This code seems to be geared towards processing and combining dataset features, while ensuring that only the data with the correct flags and labels are included in the final output, potentially for training a machine learning model or for another form of data analysis, where data from multiple sources are combined and pruned according to specific rules. This Python code appears to be part of a larger code designed for data processing, specifically for financial market data analysis. The purpose of the code is to aggregate and merge different sets of data from CSV files, likely stock market data, and organize them by security identifiers into serialized pickle files. The code begins by defining a file path where the CSV files are located and loading the list of file names in that directory. It then reads the column names from the first file to use as a template for creating data frames. It iterates over each file, reads the contents, and appends them to a temporary data frame. After every 50 files or the end of the list, it removes 2 unnamed columns and adds the clean data frame to a list. It then prints progress updates. After processing all files in the first directory, the script concatenates the collected data frames into one large data frame. It then repeats a similar process for a different directory of CSV files representing a different set of market data, possibly option or derivatives data named duoyinzi. This time, it modifies each data frame to include a trade date derived from the file name and performs concatenation every 30 files or at the end of the list. Once both sets of data are processed, the script extracts unique security identifiers SecID from the first set of data. It then loops through each unique identifier, filters the corresponding rows in both sets of data frames, and merges them based on the SecID and trade date. Each combined data frame is then serialized and saved as a pickle file, named after the unique security identifier. Lastly, the script prints out progress messages as it loops through each unique identifier, providing feedback on the number of completed tasks versus the total number of unique identifiers to process. The provided Python code performs data preprocessing, feature selection, and modeling using hidden Markov models HMMs for a dataset presumably related to financial metrics or measures. It utilizes several libraries and custom modules to process and analyze the data. Initially, the code imports necessary libraries such as Pickle, NumPy, HMM-Learn, Pandas, and others. Additionally, it imports various custom functions and modules for data manipulation and preprocessing. The script defines several functions to handle specific tasks. Load Duoyenzy single score loads pre-computed scores from a file using Pickle. Form diff type creates lists of different types of financial indicators or metrics. These are later used to filter features by their category. Type filter filters the features by selecting a subset based on a threshold. Solve1 and Solve2 performs transformations and normalizations on subsets of the dataset to prepare it for modeling. Solve on raw data invokes Solve1 and Solve2 and combines their results. Form model trains an HMM on the processed data. In the core main block, where the code execution starts, the code loads scores, filters features by type, and iterates through these filtered feature lists. For each list, it performs various processing steps, including forming the dataset, handling null values, dealing with outliers, and standardizing. It then trains an HMM for each feature subset and saves the models to a file. The purpose of the script is to take financial metrics, process them through various custom data transformations and standardizations, and then use these features to train multiple HMMs. The resulting models can potentially be used for pattern recognition or predictive analysis in financial data. The Pickle library is used for serialization and deserialization of Python objects, storing intermediate results and final models for later use. Overall, the code can be part of a pipeline for financial data analysis, with the goal of capturing temporal dynamics within the data using HMMs. The given Python code defines three functions: solve1, solve2, and solve on raw data, presumably for analyzing some form of financial dataset. These functions are part of a larger module that seems to be focused on data processing for financial analysis. The solve1 function processes the financial time series data by computing logarithmic differences in prices and volumes over specified intervals. It computes the log difference between the highest and lowest prices, the log return of the closing price over a 5-time unit period, and the log change in volume over the same period. The results are stored in a NumPy array, and a flag array is created to keep track of the positions in the time series where certain calculations are allowed, e.g. those beyond the first 5 units of time. The solve2 function takes a different approach. It calculates the ratios of different prices, open, low, high, close to the previous period's closing price. This function assumes that all data points are valid for processing as indicated by an allow flag array entirely filled with ones. The solve on raw data function serves as a wrapper that combines the output of solve1 and solve2. It calls both functions, stacks the resulting arrays horizontally, and combines the separate allow flags from each function into one flag array using an external combine allow flag function suggested by its import at the top of the code. The purpose of this code is to pre-process financial time series data for analysis. This can be used for a variety of financial analyses, such as technical analysis, pattern recognition, or building features for machine learning models. The functions handle different aspects of data processing, like feature extraction, and ensuring that the calculations done are valid for the analyzed time period. The use of warning suppression warnings.filter warning signor suggests that the developers expect warnings to arise during processing, which they have chosen to ignore, possibly due to known but irrelevant issues when processing data. This Python code defines a function, preprocessing, that computes the predicted probabilities for each component of a Gaussian mixture model GMM, given some observation sequences. The GMM is provided as an argument model, along with the observations O, a flag array, allow flag, and a list of sequence lengths. The function relies on the NumPy library for numerical operations and imports a helper function form index, which is used to determine the start and end indices of each sequence within the observations. The code iterates over the various sequences. For each one, it uses the form_index function to find out which portion of the input array corresponds to the current sequence. It then creates a subset of observations and the corresponding allow flags, which indicates if a prediction should be computed for an observation. It only computes predictions for those parts of the sequence where the allow flag is set to 1, probably meaning that a prediction is meaningful or allowed. The predictions for each component of the model are stored in an array, and the results are collated for each sequence to form the final prediction probabilities array. The purpose of this code is to apply a trained GMM to a set of observation sequences, efficiently handling multiple sequences that may have different lengths, and to determine the probability distribution of each sequence belonging to each of the components in the mixture model. It's a typical task in areas such as pattern recognition, data analysis, and machine learning, especially in problems involving sequence data like time series or speech. The purpose of the Python code provided is to predict the probabilities of hidden states in a sequence based on the given observations. The code specifically appears to implement a prediction algorithm that could be part of a hidden Markov model HMM combined with a machine learning method, possibly XGBoost as suggested by the reference to XGB in the import statements. This code defines a function called preprocessing, which takes several parameters, an initial state distribution π, a transition matrix A, observed sequences O, a model presumably trained with XGBoost, a Boolean array allow flag to identify usable observations, and lengths indicating the lengths of different sequences within O. The function calculates the probability of each state for each sequence given the observations using the provided model and the rules of the HMM. In a loop, it segments the observations and the corresponding flags for each individual sequence based on its length. For each segment, it uses the model to form a probability distribution over the states via form B matrix by XGB, and then applies the self-pred function to assign probabilities to the allowed states. The results are aggregated into a final array predproba, which contains the predicted probabilities of the states for all the observations in O. The returned array has the same number of rows as the observation sequences, and as many columns as there are possible states, with each element corresponding to the probability of a state given an observation. This Python code seems to be part of a financial analysis tool designed to process and prepare a dataset for some form of predictive modeling, likely using hidden Markov models HMM, as suggested by the directory path containing HMM code within the code. The code defines several functions that perform different data pre-processing tasks. 1. Form file path by int ID constructs a file path for a given integer ID by searching within a specific directory. If the ID is found, the function returns the file path, otherwise it returns none. 2. dfcol-qchong is designed to remove duplicate or redundant columns from a data frame. It handles columns that appear to be duplicates because they have similar names, typically differing by a suffix like x or y. 3. Replace price 0 to nan replaces 0 values with nan in specified price-related columns within a data frame, and replace vol 0 to 1 replaces 0 values with 1 in specified volume-related columns. 4. Fengby-is-open segments the data frame into subframes based on the is-open column, which likely indicates whether the market was open on a given date. It excludes segments with fewer than a specified number of observations, controlling for insignificant data slices caused by market closure. 5. Form label assigns labels to each row in a data frame based on the change in the close price over a given time frame t, where the change is measured either in absolute value or as a ratio depending on a specified threshold. 6. Array is-nan computes a Boolean array indicating whether each element in an input array is nan or not. 7. Col with high ratio nan identifies columns within a dataset that have a high proportion of nan values exceeding a given threshold. It can also persist these ratios to a file for later use. 8. Form feature name decides which column names from an initial dataset are relevant as features, excluding columns with non-numeric or identifying information and those with a high ratio of nan values. 9. Fill NA attempts to fill in nan values in an array using spline interpolation, but if the number of consecutive nans exceeds a threshold, it returns an error. 10. Tran-nan is a utility function that creates a copy of an array, ensuring that each element is either of type float or nan. 11. Form raw dataset combines the above functions to construct a dataset for model training. It processes data files associated with selected integer IDs, cleans and segments the data, labels the observations, handles nan values, and assembles the features and labels into arrays ready for use in a model. The function can also print out progress information if requested. This code performs critical pre-processing steps, such as handling missing values, cleaning up column names, segmenting data based on trading days, assigning labels for supervising learning, and constructing a feature matrix. It is likely part of a financial data analysis pipeline, preparing data for a machine learning algorithm to make predictions or detect patterns based on historical stock market data. This Python code is defining a function named bagging balance weight that implements a form of the bagging algorithm with class balancing for a given dataset. The code assumes the dataset consists of input features, x, and corresponding labels y. This function is particularly useful for creating a balanced subset of data when training machine learning models, especially when there are imbalanced classes within the dataset. The function first establishes parameters like the threshold drop th to consider when dropping rare classes and the maximum subsample ratio. Then it processes the y labels to find the unique classes and their respective ratios within the dataset. If y is a one-dimensional array, it is assumed to contain the raw label values. If y is multidimensional, it's assumed to be in a one-hot encoded format, and the code transforms it into a list of numeric class labels. Classes with a representation less than the specified drop to threshold are effectively discarded from further processing, preventing them from influencing the output. For each class not dropped, the function enters a loop to subsample from the original X dataset based on the class balance found. It generates a new balanced dataset where the number of instances from each class is proportional to the frequency of the most common class. After collecting all the subsampled instances, a final shuffle is performed so that the resulting X and Y arrays have their instances in a random order. This randomness can be beneficial for algorithms that are sensitive to the order of training data, such as neural networks or stochastic gradient descent-based methods. In conclusion, the purpose of this function is to create a balanced subsample of a dataset for training machine learning models, while also implementing a random subset selection bagging to potentially improve model robustness and performance. The result is a new dataset with balanced classes ready to be used in the training of a model. This Python code defines a function combine allow flag that takes two arguments, both of which are expected to represent allow flags. These flags are likely lists or arrays that consist of binary values 1s and 0s, indicating whether certain conditions are allowed 1 or not 0. The purpose of the function is to combine these two sets of flags into a single set, following the rule that a position in the resulting set is only allowed set to 1 if the corresponding positions in both input sets are allowed 1 in both. The function first checks if the lengths of the two input lists are equal. If they are not, the function abruptly terminates the code by calling sys.exit with an error message, enforcing that both input flags must be of the same length to be combined. If the lengths are equal, the function proceeds to create a new array initialized with zeros, having the same length as the input arrays. It then iterates over the elements of the input arrays, comparing the values at each position. When both flags at a given position are 1, the function sets the corresponding position in the result array to 1, otherwise, it leaves it as 0, indicating disallowance. Finally, the function returns this newly constructed result array, which represents a combination of the two input arrays following the described logical and operation. The output of this function can be seen as a sort of permission filter, only allowing actions or features where both sets of conditions explicitly allow them. The provided Python code defines a function named evaluatePlot that calculates and returns a score based on inputs that relate to the state of a system and corresponding labels. It uses the NumPy library to perform various numerical computations. The function receives 4 input arguments: state, end states, label, and lengths. The arrays state and label represent sequences of states and their associated labels respectively, while lengths provide segmentation info for these sequences. End states indicates the total number of unique states. In the code, various temporary arrays are initialized: accuracy, entropy, count, and record, each serving a different statistical purpose. The count array tallies the occurrence of each state, while the record array tracks the correlation between states and labels. The function iterates through the segments defined by lengths, cleaning the data by removing instances with a specific label value made as 2. Then it further processes this data to update count and record, effectively creating a frequency distribution for state label combinations. Subsequently, it computes the accuracy for each state, which is the maximum frequency of a label for a given state, normalized by the number of occurrences of that state. Additionally, it calculates the entropy of the label distribution per state, which is a measure of the randomness or unpredictability of the labels associated with that state. Lastly, it combines these metrics into a weighted score that considers the entropy, accuracy, and relative frequency of each state, providing a single numerical value meant to represent some aspect of the overall system's performance or characteristics. This score could serve as a way to evaluate a predictive model's performance or assess the quality of a data segmentation in machine learning or data analysis applications, where higher scores might indicate better model performance or more meaningful data segmentation. The Python code you provided defines a function called form_accuracy, which is designed to calculate the accuracy of a machine learning model's predictions for a multi-class classification problem. The function takes 3 arguments: x, which represents the input features for the prediction; y, which is a one-hot encoded array of true class labels; and model, which is the machine learning model used to make predictions. The function begins by initializing an array called single record with 3 zeros. This array is used to track the number of correct predictions for each class. Then, model.predictx is used to get the predicted probabilities for each class. For each prediction, it finds the predicted class with the highest probability pred class and compares it to the true class, true class. If the prediction matches the true label, it increments the count for the correct predictions in single record. After processing all predictions, the function calculates the overall accuracy as the sum of correct predictions divided by the total number of predictions. It also calculates the class-specific accuracy by dividing the number of correct predictions for each class by the total number of true instances for that class. Lastly, the function returns the overall accuracy and the array single record, which holds the class-specific accuracies. This code allows users to evaluate not only how well the model performs overall, but also how well it performs on each individual class. The Python function formIndex is designed to calculate a beginning index and an ending index based on a list of lengths and an index provided by the user. The function takes two parameters: lengths, which is expected to be a list of integer values, and index, which is an integer that points to a specific position within the lengths list. Inside the function, it first calculates the begin index by summing up all the integer values in the lengths list up to, but not including, the given index. This gives us the starting position for the slice of data that corresponds to the index. Next, the end index is calculated by adding the value at the lengths index to the begin index. This results in the ending position of the slice. Finally, the function returns a tuple containing both the begin index and the end index. This tuple effectively represents the range of positions for the sublist or subarray of data that starts right after the previous segments defined by the lengths list and ends at the length defined for the current index. In summary, this code is a utility for segmenting a sequence into subsequences based on provided lengths. It can be used, for example, to parse a serialized list of items where each item has a known length, or to divide a dataset into parts for separate processing. The purpose of this Python code is to prepare a dataset for use in machine learning or data analysis. The code transforms an input dataset based on specific criteria and compiles a new dataset that's ready for modeling. The function formModelDataset takes four parameters: dataset, label, allowFlag, and lengths. The dataset is a two-dimensional NumPy array containing features, while label is a one-dimensional array containing corresponding labels for each entry in the dataset. The allowFlag is an array indicating which rows in the dataset are to be included flagged with 1 or excluded flagged with 0. The lengths parameter is an array that presumably represents lengths or counts of data segments to be processed. The function iterates through the lengths array, and for each length, it uses formIndex to determine the beginning and ending indices of the segment in the dataset to process. For these segments, it filters out the rows where allowFlag is 1 allowed. These filtered rows from the dataset, along with corresponding labels, are added to accumulating results. Result dataset, result label, and a count of allowed entries are added to result lengths. The end result of the function is a tuple containing the newly formed dataset, result dataset, the array with the corresponding labels, result label, and the list of the number of allowed entries in each processed segment, result lengths. The filtered dataset and labels can be used for training or evaluating a machine learning model, ensuring that only data points marked for inclusion are used. This Python code defines a function called randomCut that is intended to split a dataset into training and validation sets. The purpose of splitting data like this is for evaluating machine learning models, where you train the model on the training set and validate its performance on the validation set. The split is commonly used to assess the model's ability to generalize to unseen data. When invoked, the function randomCut takes three arguments: x, y, and an optional k-fold with a default value of 5. X is assumed to be a dataset with multiple samples, e.g. images, documents, etc., and y is the corresponding set of labels or targets associated with each sample in X. The k-fold parameter is used to determine the size of the validation set relative to the entire dataset. Specifically, 1/2 k-fold of the data will be used for validation. Inside the function, it first creates a list of indices corresponding to the samples and randomly shuffles them using the random shuffle function. This is to ensure that the data is randomly sampled when creating the training and validation sets. It then calculates the index at which to split the shuffled indices into the training and validation sets. The function proceeds to split the datasets based on the calculated index. The samples from index temp index to the end of the dataset are designated as the training set xtrain and ytrain, and the samples from the beginning to the index temp index are designated as the validation set xvalid and yvalid. Finally, the function returns the split datasets, the training inputs and corresponding labels, and the validation inputs and corresponding labels. Users of this function can then use these datasets to train and validate their machine learning models. The Python code in question is a function designed to process and clean a dataset by addressing outliers in the data. The purpose of this code is to ensure that the dataset is free of extreme values that might otherwise skew the analysis. The function takes two arguments: dataset, which is the data to be processed, and lengths, which seems to be an array-like structure representing segment lengths within the dataset. The function imports necessary modules and a custom function form index, which is likely used to create indices to segment the dataset. It also imports a fill_NA function, although this is not used within the provided code snippet. The solve_on_outlier function begins by initializing a result array with the same shape as the input dataset, filled with zeros. It then iterates over the segment lengths provided by the lengths argument. For each length, it calculates the beginning and ending index of the corresponding segment within the dataset using the form index function. Inside a nested loop, the code then copies a subsection of the dataset corresponding to each of these segments and checks if there are any values greater than 4.5 in that section. It computes the mean and standard deviation of the current segment of data and flags a value as an outlier if it lies more than n standard deviations away from the mean. The value n is set to 3, which is a commonly used threshold for identifying outliers in many statistical applications. Outliers are replaced with the mean value of the segment, presumably to mitigate their influence on subsequent analysis. After processing for outliers, the sanitized segment is stored in the result array. In summary, this function is a data cleaning tool aimed at normalizing segments of a dataset by moderating extreme values based on statistical measures like mean and standard deviation. After the function has run, the resulting array should have suppressed outliers, making it potentially more suitable for further analysis. The Python function GMM-HMM is designed to create and train a Gaussian mixture model hidden Markov model GMM-HMM using the HMM-Learn library. This model is typically used for problems where you have temporal or sequential data, and you want to model states that are not directly observable, but have observable emissions that depend on the state. A common application of GMM-HMMs is in speech recognition, where the states could represent phonemes, and the observations could be features extracted from the audio signal. The function takes several parameters. O, the observation sequences to train the model. This data is typically a sequence of feature vectors. Lengths, the lengths of the observation sequences when O contains multiple sequences. This informs the model where one sequence ends and the next begins. N states, the number of hidden states in the model. This is a crucial parameter that defines the complexity of the model. V type, the covariance type of the Gaussian distributions used in the mixture model. This defines how the variance is structured in the Gaussian components. N-iter, the maximum number of iterations to use when training the model with the expectation maximization EM algorithm. Verbose, a flag to determine whether to print out progress messages during the training process. Once the parameters are set, the function initializes a Gaussian HMM from the HMM-Learn library with the specified parameters, and then trains it on the provided observation sequences O, using the lengths to correctly parse the sequences if necessary. The trained model object is then returned. This model can be used to predict the hidden states for new observation sequences, or to generate new sequences of observations that have similar statistical properties to those it was trained on. The given Python code describes the process of training a deep learning model, specifically a long short-term memory LSTM network, for some classification task. The code makes use of Keras, a high-level neural network API, which runs on top of TensorFlow or Theano. First, the code imports necessary libraries for numerical operations, machine learning model building, preprocessing, and utility functions, which seem to be custom functions not included in standard libraries. The form LSTM dataset function appears to take in a set of features X, a set of labels Y, a list of sequence lengths, and a window size T, and transforms the data into a format suitable for training an LSTM network. This involves segmenting the input data into subsequences of length T. The main function self-LSTM preprocesses the input features using min-max scalar to normalize the data. It then uses the form LSTM dataset function to convert the data into the LSTM format. The labels are binarized using label binarizer, implying a classification task. The data is then split into training and validation sets via custom function random cut, and training data is balanced using bagging balance weight. The code then defines the LSTM network model with several layers, including dropout layers to prevent overfitting, batch normalization layers for faster convergence, and dense layers for prediction. It uses a leaky ReLU activation function for the hidden layers and a softmax activation for the output layer to handle the classification. The model is compiled with the stochastic gradient descent SGD optimizer to minimize the categorical cross-entropy loss function, a common choice for multi-class classification tasks. The model is trained using the training data with a specified batch size and number of epochs without using any early stopping or other callbacks. After training, the accuracy of the model is assessed on both the training and validation datasets with a custom form accuracy function. Finally, the min-max scalar and the trained LSTM model are saved to the disk at specified locations with file names incorporating an external variable file name, indicating that the model and its scalar can be reloaded for later use or analysis.